All right, continuing pretty much where I left off because the phone storage was full, so I went and deleted about 20 gigabytes of video and went on to record one of these videos, which is about another gigabyte or two for whatever reason. Because it's audio only, it's barely several hundred kilobytes, I imagine. So, in reading about the plane curves, then it was described for some of these theorems of the plane curves with respect to the symbolic expression of any geometrical problem that involves directly or indirectly the gradient at the point is in fact a differential equation of the first order. Catching up, it may, however, be of higher degree than the first, but for the moment, problems that lead to equations of the first order degree will suffice as examples. If P be any point x, y on a plane curve, let T and G be the points at which the tangent, ordinate, and normal, with regards to whether the n is the normal, or otherwise that it seems incongruous for that as the variable name when it doesn't match the name. There's not really a name for ordinate, or maybe these are named for Latin names or German names or something like that. That these at P respectively meet the x-axis. That if psi is the angle between TP and the positive direction of the x-axis, y prime equals tan psi. So what was read into this was this idea that, according to this kind of three-quarter turn curve thing in the y model, that this line connecting the simple points about reflecting and the symmetrical about x equals y, or the line from the origin at 45 degrees or pi quarters radians, this goes off to infinity, symmetric about that, then that what would be normal to that and going through 1, 1 would with intercepting at 0, 1 and 1, 0 and filling that in, that either way, what would be its y prime of the circle at that point would be tangent of psi, which is, in terms of that line, for the function of the line, or just expressing this plane curve, only about that fx equals y, or rather x equals y, fx equals x, that tangent psi so results as a simple example of showing this. So then the gradient may be introduced indirectly. Now, I don't recall really going into this and over this before, but I've almost certainly heard these terms if they're very common about the plane curves. About the subnormal equals NG, the line NG, equals NP tan psi equals y prime equals y dy dx, so that y prime would be in here that it's just y equals x, and so y prime would just be x equals y dy dx, which is x. So that's the same. And that tangent psi equals 1 because the angle here is 3/4 pi. And then similarly for subtangent, because both of them are about the, that sine and cosine, and about 1 over root 2, often written as root 2 over 2, just because writing 1 over root 2 is kind of unfamiliar to people, or 2 to the negative 1/2, whereas writing root 2 over 2 then leaves it very usual in lots of trigonometric identities and such. So anyways, here this for sine and cosine for that. It's for the 3/4 pi, it's 1. For tangent and cotangent, just showing that this lines up really neatly indirectly with reductions in trigonometry about positive numbers. And there was some interesting commentary. I'm not sure if it was caught that it was about the when you only have positive numbers, you don't really need imaginary numbers to make complex numbers, because you can just use the negative numbers, which don't exist. The lengths PT, PG are known as the tangent and normal respectively. They involve y prime, but not linearly. Tangent length and normal length. Example 1, curves whose subnormal has the constant value 2a, y prime equals 2a, or y dy equals 2a dx, integrating y squared equals 4a times quantity x plus c, which represents a family of equal parabolas with axes coincident with the x-axis. All right. So here it's generally defining, that f of x is the independent variable, but here it has that the variables are dependent with respect to each other in this plane curve trigonometry, and why and how that trigonometry could also be written in other forms of functions that make it so that these angle relations hold true. other kinds of orthogonal functions that make for plane curves, such usual things of these integral curves. And so today we talk about things like superposition of all the integral curves. And you can solve them linearly because they're up in our vector space and this and that. And there was mentioned, you know, the great facility of our vector base and our vector space and how it works to make all such manners tractable to linear algebra and eigenvalue problems. And after linearity for superposition and all these methods of infinite sequences that we can use to at least crunch the first few and get a close approximation, or at least an approximation. But here, though, it's a bit more the geometric, as the author put it. The first order degree will suffice as examples that the gradient at any point is in fact a differential equation, and that as it was said, that it was geometric or other. The reason why is equivalent to the geometrical problem about these parameterized curves in terms of the equation, and then finding the functions in terms of each other that are not linear because they're each in terms of each other. But it can be kind of nice when it's like this and it's just not the usual approach, but it seems kind of nice. Curves whose subnormal has a constant value. Example 2. Curves whose subtangent has the constant value a of y of dy to the dx equals a, or dy over y equals dx over a, or y 1 over y dy dx equals 1 over a, or y dx dy equals a. Integrating, log y equals log c plus x over a, or y equals c e to the x over a family of exponential curves. So those are most familiar when people say, oh, I have an integral and it's a differential equation. I'm pretty sure that I'm going to find the exponential in that. Or about when, or that the logarithm of y equals x, a family of exponential curves. So here is describing in terms of the subnormal and subtangent curves that have these as constants in there. So they're kind of like lines, but they're otherwise the things that look, for example, like the parabola and exponentials that can be solved kind of in neat little ways. And here, as I'm kind of framing it, is about this shrinking the quadrant to the square bit. Is the idea then that as it does so, it will maintain that from the corner and the origin through to the end of the square, the other side of the square, the opposite vertex, is on the line x equals y, and all these functions are symmetrical about it in the box as it's shrunk. So this is the kind of thing that I've been thinking about with regards to differential equations, in terms of finding out who already did all this kind of stuff and set it up. And it might have been somebody who said, well, I kind of gave up when they said it was non-standard because I knew if I tried to write it up, they would call me non-rigorous because I don't have a rigorous non-standard. I worry about that less because I have a rigorous non-standard. So I feel a little bit more free than some people. By the same token, there are probably all kinds of mathematicians, like in the 1600s, this is their bread and butter, this is their daily. They just kept it in a little journal and it's used all the time. It's like, do you know where empirical formulas come from? Oh, yeah, whatever works. Whatever works. Curves in which the subtangent is twice the abscissa. This is about the ordinate side of y dx dy equals 2x. The variables are separable. The integral curves are the family of parabolas, y squared equals cx. And here we're kind of trying to frame things sometimes in only positive x and y. Figuring that if anything is in bounds, and then in terms of what's defined by, oftentimes you can express things only in terms of positive numbers. Not that there aren't negative numbers, but just they involve any kinds of reflections and symmetries and these kinds of things as about being translated and transformed and defined and this and that. But here we're just using an orthogonal basis to make a symmetrical basis in a sense. In coordinates that just have that, and is a sort of, there's sort of a subcoordinate, I guess you'd call it, and it's so under the x and y coordinates, there's this coordinate as an angular distance on one of these plane curves that is a circle, or otherwise any one of these plane curves that are symmetrical on either side that has an angle and then as a distances along that curve. That could be very useful. It's used in off imagining, you kind of look left or right and it's like, well, that's parallax for you. Curves in which the subtangent is twice the abscissa. Variables are separable, so it's like integration by separation, and then solving them as each is first order in degree by these plane equations, the parabolas. So this is nice. It's helping describe, especially for regular plane curves, what are integral forms that have them, and then to figure out how to write stuff in terms of those because it's given. Example 4, the ordinate at any point, and what's happened a lot is like, how was this formula equation written? It was written in terms of the expressions that are given. The ordinate at any point is equal to the perpendicular from the origin to the normal at that point. Ordinate. So this is a plane curve where the ordinate at any point is equal to the perpendicular from the origin to the normal at that point. So it reflects that it's kind of like a triangle. I mean, whatever bounces off and makes incident off the normal, it drops down the origin, and those would be so it's kind of like where the angle from the origin to the point on the line is such that it reflects and drops straight down. If xy is any point on the normal at xy, then big X, if big X comma big Y is any point on the normal at xy, then big X plus big Y, y prime equals x plus y prime, and therefore the length of the perpendicular from the origin is x plus y prime over root quantity 1 plus y prime squared equals y. Wow. This symbolic statement involves y prime squared as it stands, but on rationalization and simplification, it reduces to an equation of the first degree in y prime. So that it involves y prime squared is saying that it's not first order, but rationalization and simplification, I'll need to consult what he means by rationalization, where simplification is algebraic manipulation to reduce terms usually. It reduces to an equation of the first degree in y prime. X squared plus 2x y prime equals y squared. Or 2xy dy plus quantity x squared minus y squared quantity dx equals 0. This can be integrated as an equation of homogeneous type, section 4, example 1, which is given later, I imagine, in chapter 4, example 1. Or that was given in example 1. There it is. Terms in the equation are homogeneous and of the second degree in x and y. The above process is therefore applicable. Above process being separating the variables and integrating. The homogeneous type, because p of x comma y dx plus q of x comma y dy equals 0. So it's one of these plane curves. And in fact, all these kind of curves are in as of this type. So any of these plane curves as integral curves is kind of as this homogeneous type of the equations. Separating the variables and integrating, where R and S are independent. So he's just explaining that then for these forms where the on the plane curves, for these ones that kind of been having these properties have been kind of just generally developed, and I imagine that they're very usual in lots of usual analytical developments, if not necessarily the first course, because they're not necessarily generally extensible or applicable to the wide, wonderful world of differential equations. But they start, and they might begin, and therefore the length of the perpendicular from the origin is da da da. This symbolic statement involves that, so it reduces or 2xy dy plus quantity x squared minus y squared quantity dx equals 0. And I'm always interested in x squared minus y squared, and also x minus 1 times y minus 1, and so on. But here, this can be integrated as an equation of homogeneous type, or as one which has, for an integrating factor, a function of x alone. For an integrating factor, which I'll need to understand. The second method is the simpler. The integrating factor x to the negative 2, or 1 over x squared, leads to the general integral x squared plus y squared equals cx. So integrating factor seems as described usual substitution by variables in a very particular elementary form, so that substitution by variables as an integrating factor kind of has a thing. Leads to the general integral x squared plus y squared equals constant x, representing a family of circles touching the y-axis at the origin. So we went from a family of circles centered at the origin to this one where it's very familiar as the parametric curve of the origin. This differential equation, it has a solution of a family as by a circle, and it's this so that is the perpendicular from the origin normal at that point. So I was trying to think of a very abstract curve which has had this property that it reflects as of the normal of it down to the ordinate, and it's a circle. In terms of that, the normal will always be less than pi quarters, in a sense. Section 15, trajectories. Let f of x, y, and a equals 0. Or x, y, and alpha, I suppose that's a. X, y, and a equals 0. I know it's alpha because and g, x, y, beta equals 0. F of x, y, a equals 0 and g of x, y, beta equals 0 be the equations of two families of curves, each dependent upon one parameter. When each member of the family beta cuts every member of the family alpha according to a definite law, any curve of either of the families is said to be a trajectory of the other family. So here this is helping explain when these curves come together and they're symmetric about x and y. And so at some point in time, if they cross x and y, this is where the trajectories of each other. The most important case is that in which curves of the families intersect at a constant angle. So I'd be trying to figure out how to make it so that the angle is so conserved both for this about x and y and curves symmetrical about x and y that cross x equals y, and that their angles as their incident so are constant for all the family of curves, and also when it's shrunk or when it's shrunk from the quadrant to the unit square, that it also is so, or when only one or the other of those is so, because then that would call them the most important case is that in which curves of the families intersect at a constant angle. When a curve intersects all the members of a family of curves at right angles, it's said to be an orthogonal trajectory of that family. So when it says orthogonal trajectory, I immediately think of that in terms of orthogonal functions when their square is, or their product is 0, or that they're orthonormal, and when their outer product or some convolution or involution is 1. Thus, any circle of center O is the orthogonal trajectory of the family of straight lines radiating from O. And conversely, any line through O is the orthogonal trajectory of all circles concentric with O. The there could be others is a very contrived kind of function, and for only a subset of the circles. Like for example, you can imagine a wave through circles out of the Archimedean spiral, or out through these things that would have a function that arbitrarily is like so. It's just how so it arrives at they're orthogonal, keeping in mind that sine and cosine are orthogonal functions. Are the trajectories of each other? I suppose kind of so. I'll be corrected if I'm wrong, and any mistakes are my own again. Thus, any circle of center O, that is the families x squared plus y squared equals a squared, or alpha squared, y equals beta x, are mutually orthogonal. Circles in that form, with according to the radius, and lines in that parametric form with no intercept, in rectangular coordinates, let p of xy dx plus q of xy dy equals 0 be the differential equation of one family of curves. When written in the form y prime equals negative pxy over qxy, it expresses the fact that if an integral curve passes through xy, it will have a certain gradient at that point. The gradient of the orthogonal curve through that point will be the negative reciprocal. See, this amuses me a lot because it helps when you're talking about like the tangent and the normal. They're perpendicular to each other, they're orthogonal to each other. And whereas orthogonal also means 90 degrees in pi halves radians. Computing the gradient then, and the gradient is very overloaded terms because it means the means of steepest descent. It means the slope. It means sometimes it's considered to be some of the partials about just whether that is what's computed to is leave it like so, and as it's so contained, it describes condition. But it means the differential, and so it's nice to think about that in terms of this, because I want to figure it out for a curve of arbitrary dimensions, that its gradient is its direction, and the idea is that these plane curves can have this figured out for these pretty simple curves for that like so, and then I want to integrate those and then solve for those their differentials and compute their gradient, because it will indicate optimizations. In other words, an orthogonal trajectory would be an integral curve of the differential equation pxy dy minus qxy dx equals 0. Moreover, whenever an integral curve meets an integral curve of and so that's minus. So wait, pxy dx plus qxy dy equals 0, and then pxy dy minus qxy dx equals 0. Moreover, whenever an integral curve of 15.2 meets an integral curve of 15.1, it will cut it at right angles. Given that it's orthogonal about these curves and the trajectories, that this is an identity, what so results because it's so. So these are great things to know about in terms like the frequency and spectrum analysis, which take a lot of higher level order differential equations to get to, in terms of just kind of geometric approaches, and then when we talk about maybe the spherical and planar curves are a little neater than I thought. I never got into enough because I'm looking at these now as kind of some unimportant complements and complementary duals to things that are singular or inscrutable or intractable in ODEs as let's see, what's the way to put it? Not plane curves, but as functions in a sense, but as inseparable, or when it's not parameterized in terms of both of them, so that they're first order ordinary and is tractable to linear methods and particulars. That this is important complementary dual of these systems, and the fact that there are so many systems of normal functions or orthogonal functions or orthonormal functions, pairs of these functions that establish these systems, that you can find something in terms of one, if you can figure out to find in terms of this other one, these functions, that they make all these complements and make for infinite series that add them up and makes for systems of transforms and dot, 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 make for integrals like this, the integral of 1 over x is ln x and this kind of stuff. And how that's so, for example, as it goes from 1 onwards in the x-axis, and so it's so for the same region as it goes for 1 upwards in the y-axis for this function that's symmetrical by x and y. And then you can separate any of these functions, they're x symmetrical by x and y in terms of where they intersect together. The function x equals y and the positive numbers, and compute what's underneath that point as a square, and what's above that on one side as an integral, and what's above that on the upside is the same. It makes for a sort of extra kind of analysis, because you think of Riemann analysis and his vertical rectangles vanishing width with their analytical character. You think of Lebesgue analysis, and it's kind of like horizontal rectangles of vanishing height. And then Stieltjes, it's kind of them together. So it's kind of like Stieltjes in terms of then they figure out for these classes of functions, if you can frame it in terms of these functions that are like so, then you can frame it in terms of the sums and differences of these functions on the positive numbers like so. It results in cheap analysis. Well, that's what I was getting into today. As I've been reading about the, here we go, this Fourier analysis and boundary value problems. And here's something like my Emery-Lakatos proofs and refutations. And what I've been trying to figure out, in the Fourier analysis and boundary value problems is recalling my instruction that I've already gone through, and I haven't had too much use to make of it, but it's always been available as something that taught me basically about orthogonal functions and systems of transforms and the availability to find for any system orthogonal functions of transforms. And so what I'm always looking out for when I'm trying to figure out things mathematical in the standard and non-standard is to look for these complementary duals. And what does it mean, a complementary dual? Well, it's very much an example itself, that kind of system. What adds up that you can have the tangent and normal. They're complementary duals, in a sense. And so trying to figure out then how they add back together and make an analysis, a synthesis, is very much a key kind of thing. And then there's also about the extensions beyond those. Well, what about a family of 3 functions? Kind of like this talk started with like the talk of symbology of numbers, and the lucky and unlucky and what. Well, then there's if we get into higher variables instead of plane curves, if we get into volume curves, when and where and how do these higher level analogs hold up and show up, and can we use it to compute the gradient for lots of different neat simple forms of dynamical modeling like so. It's like, well, all I know is we have 10 billion points and we just need to integrate them and end up finding out this and that. It's like, well, all right, well, hey, maybe then we can just figure out, if you need to do model fitting, at least we can provide about 1,500, 2,000 different symmetrized, normalized shapes and scale distributed type of distributions, and over each of these regions, or your means and your averages and your clusters and stuff, you can add those up and see if they drop down through the tractable bank and work out and make big hits on those, and see that then you can add up those for less and making just computing a field of small differences instead of positive and negative numbers everywhere, Maybe it could be so like that. And then there's also the idea that kind of like for Riemann and Lebesgue and Stieltjes, I'm thinking about this idea that there's mensuration and integration only in the positive numbers, and it starts in the planar, and then it'd be important to have like a linear analog, which would be like what? It's like, well, it's a straight line and then it has a curve, so it's piecewise. And so if you take the line integral of that, it should add up about the same. That here, the idea is to figure out if you want to compute the area under these functions, the definite integral of all these things, that then you can figure out at least some of these functions, a form like that, and then define other functions in terms of sums of those, and infinite sums and series of those. So yeah, that's interesting. Just think about a little branch of differential analysis. And so I'll be studying the plane curves and their integrals a little bit in the history of that. Because I imagine that where those were, of course, that was part of the direct instruction, but it hadn't been invented that long, so it was still kind of the realm the historians of mathematics and its development. But and it was kind of abandoned because it didn't end up becoming tractable for people. It was like, hi, it's the 1970s and I need to learn Fortran because to compute how many truckloads of train cars of this plastic we need to make enough vinyl for these records, I need to compute one thing, and I'm going to use this code and I'm going to use this computer to do it because it has too many variables. And ever since then, it's been stuff that's kind of designed to get into it, and we want to organize that. And these days, with like differential geometry, that's going to see a big upswelling because it's also going to offer us like, hey, with these, not only can you crunch them and continue them, but also if some of them are closed, so finally we can stop. These are some kinds of things going on. So I'm going to be looking some more at these plane curves and for some methods of analysis to make some closed forms. Closed forms are always good. And also about this non-standard bit, because I have some non-standard tooling that I'm able to apply about, what function is its own antiderivative? There was a joke about a function in the spiral space filling curve walked into a bar. And it was like, do you want to hear a joke about a function that its own antiderivative? And it was like, don't laugh at me, And everybody's surprised because he wasn't exponential, I thought the exponential was the only function that was his own antiderivative. Oh. So these are the kinds of things that I want to figure out in terms of, the integral and mensuration. And then in terms of like, hey, well, Dirac's delta, well, how about Dirac's horizontal delta? What's that? Is x equals y? Yeah. Y equals x. Oh. Is that an even function? Oh, there aren't any even negative numbers at all. Whoa. Well, there are, and you can, but you can go there, right? So that being kind of the idea of why last time I was kind of taken with the idea of 1 over x and shrinking the quadrant to the square and calling that a scaling of it, that a scalar, this infinity. That the idea that infinity is a scalar is that you can point at it, and if it came all the way, if it scaled the world all the way into where you point at something that this otherwise was before the finite distance away, it's scalar infinity. It's actual. Hey, have a great day.